Hi everybody, welcome back again. This example 9.2 is a conceptual one in that we don't have any numbers to put in and calculate, but it is a good sort of thought experiment when talking about impulse. As we mentioned one or two video segments ago, we described impulse as force times a change in time. All right, the impulse applied is force times a change in time, which means that for a given impulse, as force increases, time gets smaller. As time gets smaller, force increases. The other thing we said was that impulse being force times time is also force times time can be known as change in momentum. All right, I should probably put a vector arrow over the F and the P right there. Okay, both of those things are true. So here we have a lady out in the rain. She's holding an umbrella, and we're comparing what happens when raindrops fall down and hit the umbrella, right? Versus if maybe a few minutes later it gets colder and they turn to hail, all right? And hail comes down, or sleet, that is ice pellets, and come down and start hitting their umbrella. And you can see in the diagram right here, she's got a very different kind of body posture versus right here. And so what it's asking me is the force required to hold the umbrella up more, less, or the same as the force required in the rain? Well, again, as I mentioned, I think the image suggests what the answer is, but what's actually happening right here that could kind of give us a clue as to what's going on? Well, let's say we have, and I'm wondering if you can see this. Can you see that coming down? Yeah, I made it blue because of rain. All right, so say you got raindrops coming down. All right, and there's a raindrop right there, and it comes down and strikes her umbrella. What's the raindrop going to do? What do raindrops often do? They oftentimes just sort of run down the umbrella and then drip off the end, right? So let's say your initial velocity right here is 5 meters per second. We're calling down the positive direction, all right? And maybe once it hits the umbrella and kind of runs off, as it's running off, it has a less velocity, but it's still sort of in the same direction. So I don't know, we'll say 3 meters per second right here. All right, the umbrella has caused the velocity of the raindrop to go from 5 to a little bit slower as it runs down the umbrella. All right, well, what's happening on the right-hand side? Here we have a hailstone coming down. All right, say it's coming down the same speed. All right, 5 meters per second. That's our initial velocity right there. All right, well, what happens with hail when it hits something like an umbrella? Well, hail is hard. It's frozen water. All right, and so if it hits the umbrella, what's the umbrella going to do? The umbrella is going to cause it to bounce up, and that's what we oftentimes see when we see hail falling. It strikes objects and bounces up because it's rigid, it's hard, it's frozen water. So the final velocity after hitting the umbrella is bouncing back up. So as I said before, if we call the down direction positive, right, and the up direction negative right here, the raindrops come down with a 5 and they slow down to 3. Here, what the hail does is it turns around and has a negative velocity. I will say negative 4 meters per second. It's bouncing up, not quite as fast as it came down, but the umbrella is causing it to change velocity. So first of all, we have a greater velocity change, right? Your velocity final equals 5, right? 5 meters per second. And our velocity initial equals 3 meters per second. What was that right there? 3 meters per second. So that'll be a change of 2 meters per second. But over here on the right-hand side, if our initial velocity is 5 meters per second, and our I had that backwards. I had both these backwards. Sorry, this first one. Final was 3, initial was 5. Right, I'm trying to do these ad hoc problems in my head right here. Final minus initial, yes. And so here on the right-hand side, we have our our final. Again, it's always final minus initial. That'll help you to remember it. Just kind of write it down first. Final is -4 All right, and then minus our initial velocity is 5 meters per second, right? What change is that? Negative 4 meters per second. There we go. So initially we had minus 2 meters per second change. Here we got negative 4 minus 5. That's going to be a minus 9 meters per second change right there. So there's going to be a much greater change in velocity here because these hailstones are coming down and bouncing off, all right? That change in velocity, greater change in velocity means it's going to be a greater momentum change right here, all right? It's change in velocity. Delta V equals negative 9 meters per second. Here, our delta V equals negative 2 meters per second. All right, so with a greater change of velocity, you've got a greater momentum change, therefore a greater impulse. You can also think of it like this. On the left-hand side, we have impulses, force times time. Excuse me. So for any given impulse, that is the force applied over time to hold the umbrella up, to hold it against these falling raindrops or hailstones. Well, which of these two things spends more time on the umbrella? A raindrop or a hailstone? Well, a raindrop comes down, it might splatter a little bit, but then sort of runs down the umbrella. All right. By contrast, a hailstone comes down, and like I said, being hard, being solid water, it spends very little time in contact with the umbrella, and just bounces right off. So, if our time is decreased, so here we got less time here, smaller amount of time, greater amount of time here. If our time is decreased, what's going to happen to the force? Well, again, for a given impulse, if that decreases, that has to increase. So for the smaller, we have a lesser change in time. Here we've got a greater, do I have it? Greater change in time. We're going to have less force. Here we've got a smaller change in time, so lesser change in time results in a greater force, and so it's going to be much more taxing for her to hold onto the umbrella to hold it against all these falling hailstones than it is from raindrops. Even if the raindrops and hailstones have the same mass and the same initial velocity, because of the way they interact with the umbrella, it's going to result in a greater force being applied down the umbrella stem to the lady here, and much smaller force applied to the lady right there underneath the rain. Okay? All right, so that's going to be it for that segment right there, and we're going to pick up with an actual example of impulse on the next one. So thanks for following along. I'll see you on the next one.